Welcome to Let's Do It 517 and the video on linear transformations. So what is a linear transformation anyway? Well, let's take a look at a set of data here. Say, for example, you were in a chemistry class and you collected the following data, all these temperature data in Celsius. So what we like to start off with is go ahead and find the mean and the standard deviation of these particular data. So to do that, we'll go ahead and get our calculators out. And we'll go ahead and enter those data, go into Stat, go into Edit, and we'll enter in all those temperatures into L1. So let's get a large screen for just a second so we can see them here. So I have to kind of drag it over off here to the side so I can see my numbers. Okay, and looks like what we're going to do is put in 40, 41, 39, 41, 41, 40, and 38. Okay, so got those 7 temperatures all entered into our calculator in Celsius. Now what they want us to do with these is these 7 values, right, is they'd like us to find out what the mean and the standard deviation of these 7 values are. Well, to do that, let's go ahead and come back so you can see a little better what I'm doing here. What we're going to do is go ahead and go to Stat, go to Calc, go to 1var Stats, and then hit Second and L1. And notice that says, go find me the summary statistics for the list of data that's living in L1. Hit an Enter, and we should get a mean, an X bar of 40, and a standard deviation, if we go out 3 places, of 1.155, okay? Rounding off to 3 places there. In a minute, I'm going to show you we're going to hang on to that standard deviation to all 12 of the places. There's a place where that's actually stored in the calculator every time you do a 1var stat. Okay, so let's get the calculator off to the side here, and let's go ahead and write that information down here. So the mean and the standard deviation here. So let's see, actually I think I'm going to do it with the pen today so I can show you what it looks like here. So since this is a sample set of data, I'm going to use X bar to represent my mean. So X bar is equal to 40. And since I have a sample standard deviation, I'll use a lowercase s. And if you want to, you can put a sub x, but you don't have to. You can just put an s there and that's fine. And we'll go out to 3 places just to write it down. So it's 1.155 rounded out to 3 places. Okay. All right, so accomplished the first part here. Now what do they want us to do? Well, they say, what about Fahrenheit? So we're all a bunch of gringos and or Americans, and we work in this Fahrenheit schedule and not the sane way of doing a Celsius like the rest of the world. So let's go ahead and convert all of our data into Fahrenheit data, and then let's take a look at the mean and the standard deviation with that data converted into Fahrenheit. So to do that, I'm going to show you a very cool trick on the calculator here. We're going to go back into Stat, go back into Edit, and what we have here in L1 is in Celsius, but if we scroll over to L2 and get on top of the name of the list, notice that the name of the list is highlighted, I can actually enter in this formula, 9/5 C plus 32, into that list, and by doing that, what I'll end up is getting a new list all in one fell swoop. It's very cool. So watch what I'm saying here. So take 9/5, right? See, go back over the formula. Say 9/5 of what? Well, 9/5 of the temperature in Celsius. Well, where's the temperature in Celsius living? Well, that's in L1. So I'm going to go second and a 1 to get L1. And then I'm going to add to that 32. So notice that's my formulas. 9/5 C plus 32. Now hit an enter and watch what it does. Voila, all 7 scores are now instantly translated for us into Fahrenheit. That's a very cool thing, isn't it? Okay, so what they'd like for us to do is that once we've got this new list, let's go ahead and get this off to the side here, is they want us to find the new mean and the new standard deviation of that, okay? So to do that, we're just going to go back in to Statistics here, go over to Calc, go to 1var Stats, but this time our list doesn't live in L1, it lives in L2, so let's do a 1var Stats in L2. And I get the following data. I get X bar is 104, and I get the standard deviation is 2.0784. Okay? Well, let's see. Let's take and write those numbers down. because they asked us to do that anyway, right? Okay. So over here we've got x bar. Actually, you know what? I'm going to back up for a minute here. I just thought of something I wanted to do here. Let's delineate these so that they make sense. Let's make this x bar. How about x bar sub f? Excuse me, not x bar sub f. X bar sub c. My silliness here. And I want to make it so it's with respect to Celsius, because this is the Celsius data. So let's make this x bar sub c and s sub c. Okay. All right. Sorry for the confusion there, but we're back on track now. So x bar sub f, that's the mean of the Fahrenheit data. That turned out to be 104, didn't it, right? So that was 104 degrees Fahrenheit. In fact, we could even maybe mark that in there to help us understand which ones were which. And then the S sub Fahrenheit is going to be equal to 2.078 degrees Fahrenheit. Okay. All right, so let's go back here just for grins, and let's do the same thing here. Let's label these dogs in their proper units. Okay. All right. So now that was all fun, well, and good, but what was that all about? Well, here's the thing that that we want to show is that I got these values of 104 degrees Fahrenheit and 2.078 degrees Fahrenheit by first converting all the data using this linear function. Notice, if you recall a little bit from your algebra, that this is a linear relationship between f and c. Okay, so this is what we refer to with respect to data. That was a linear transformation that we performed upon our data. Now, one of the cool things about whenever you perform a linear transformation about your data is the following. If the transformation was linear, then I do not need to pump every one of the data points through the transformation. I only need to pump the mean and the standard deviation through the linear transformation with a little adjustment for the standard deviation in order to get the new mean and the new standard deviation. So what do I mean by that? Well, look, we know that the mean for the Celsius was 40 degrees, wasn't it? So if I take 9/5 times 40, which was the mean in Celsius, and add 32 to it, I get back the mean in Fahrenheit, which is 104. Okay, now if I take the mean, the standard deviation in Celsius, the standard deviation in Celsius being 1.55, okay, and I add the 32 to it, that's not going to work, okay? So I'll let you know up front, you don't do that. Instead, all you do is just multiply it by its slope. So if I take 9/5 and multiply that by 1.155, I get roughly the standard deviation that I got back. Of course, there's some round off here. The standard deviation that I got in Celsius, right? Excuse me, from Celsius to Fahrenheit. Okay, so, all right, enough of this. Let's get the punchline here. So here are the rules for linear transformations. It says let x represent the original values. X is the average. That bar keeps falling off when I transfer these over. X bar is the average of the original values, and S sub x is the standard deviation of the original values. Then, if the new values are a linear transformation of x, in other words, if y equals ax plus b, this right here is your old pal y equals mx plus b. In statistics, we use a for m. Just get over it. There's nothing you can do about that. It's not something we can argue with. Then the new mean is given by y bar is equal to ax bar plus b, and the new standard deviation is given by s sub y is equal to the absolute value of the slope times s sub x. All right, so what the heck does that say? Well, let's go back and take a look and show you what I just did here. So what I did is I took what my original mean was, 40 degrees Celsius, and I pumped it through the linear transformation being 9/5 c plus 32, and I got the new mean. All right. Notice I took my original standard deviation, 1.155, and I multiplied that by the absolute value of the slope, and I got 2.079. Now, why the absolute value of the slope? Well, if you had a negative slope on your linear relation, you can't multiply the standard deviation by a negative number and get any sort of reasonable answer. Well, why is that? Well, recall from our previous discussion, the standard deviation is the average distance away from the mean, and so it must remain a positive value. So when you grab the standard deviation, you just make it positive. That's all you got to do. Okay, excuse me, the slope. All right, so let's go up to LDI 517, which is on page 340. Standardization, a special transformation, okay? So let's perform a special transformation. Again, it's going to be a linear transformation on the data of the number of children in a household. So the first step is going to be subtract the mean from each number in the list. Then the second step is going to divide the difference by the standard deviation. So what we want to create is a new list. We'll call it, say, L2, where L2 is going to be x minus x bar. In other words, each of the data, subtract its mean, divided by S sub x, the standard deviation. So the first step was subtract the mean from each of the numbers. The second step was divide the difference by the standard deviation. Then we're going to calculate the new mean and the new standard deviation. Okay, now we're going to do that just like we did with the Fahrenheit and Celsius example. Okay, so our first step is going to be to put those numbers into our calculator. Okay, so let's get over here so we can see these are number of children per household numbers. So let's go into Stat, let's go to Edit, and let's go clear out L1, and let's go clear out L2. And we're going to go put these numbers in. So we got 2, 3, 0, 2, 1, 0, 3, 0, 1, and then last but not least 4. Okay. All right. So let's see. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep, got 10 numbers. Got 10 numbers in there. Okay. See, my 10th number was 4, wasn't it? Okay, so now what they want us to do is go create a new list over here in L2. So we're going to do the same thing like we did before. We're going to follow their instructions here. So our first step is going to be to subtract the mean of L1 from L1. All right, so open a parentheses. Let me pick this on the big screen for you so you can follow me a little better here. And put in L1. So notice that's all of my x values. So L1 represents my list of x's. Now what I want to subtract from L1 is the mean of L1. Now here's another very cool thing. If you go into second stat, you'll find, if you cruise over to math, you'll find operator number 3 in this list was the mean. Okay, so let's go ahead and grab that. By the way, this was in the list menu. This is second stat. Okay, so subtract from it the mean of L1, close off the parenthesis, close off the parenthesis. Now we're supposed to divide by the standard deviation of L1. Well, if the mean of L1 lived in second list, right, then I'll bet you the standard deviation does too. So hit second, hit your stat key to get in the list menu, go on over to math, and sure enough, option number 7 is the standard deviation of a list. So I want to take the standard deviation of L1, close off that parenthesis. Okay, now if you did this correctly, every one of these data points will now be transformed by that linear transformation. Okay, so let's go back just for a second and show you that what we did do was a linear transformation. L2, the numbers we put into L2 were x minus x bar divided by s sub x. Let's rewrite that for just a second. So what is that? Well, that's 1 over s sub x times x minus x bar over s sub x. Okay, now look, what that's telling me is this. There, change color here for you. Bar, that's my slope, that's my a. Okay, well, what's that? Well, that's my b. In other words, this fits the form we said a linear transformation has to look like. It's got to look like ax plus b. Okay, where actually you've got a negative for b in this case. B is a negative value, all right? Okay, so back to the calculator here, because what they want us to do once we did that transformation is they want us to calculate the mean and the standard deviation of this new list L2. So let's go ahead and do that. Let's go to Stat, let's go to Calc, let's go to one of our stats, let's go to one of our stat of L2. And the mean came out to be 0 and the standard deviation turned out to be 1. Now, here's the big fat hairy deal what this whole video is all about, is that's going to be true no matter what data set you put through that linear transformation. By pumping a data set through that linear transformation, you will have transformed it or standardized it, is what we say, into a standardized distribution where it will have always its mean will be 0 and its standard deviation will be 1. So here's the punchline. If we want to standardize a set of data on the same scale so we can compare the data that might be in differing units, for example, SAT and ACT scores or IQ scores from differing age groups, anything like that, in other words, we've got data that are in different scaling, then to get them on the same scale, we're going to calculate what's called their z-score or their standardized score. And what you do is you take each one of the data points. That's the data set right there. That's all the data. Let's put this in here. These are your data points. So you take the data points, and what are you going to do with those? Take each one of those data points, and you subtract from them. This is what? This is going to be the sample mean, isn't it, right? Okay. And then once you've done all that, what do? Well, you're going to go ahead and divide it by what? Who's that down there? Well, hopefully at this point you remember that that's the sample standard deviation. You're going to find out we're going to start getting lazy right now. I'm going to start getting lazy to begin with right here. We're going to start abbreviating standard deviation as SD. Okay? All right, so no matter what distribution you pump through this linear transformation, you will end up with a mean of 0 and a standard deviation of 1. Okay? All right, that's enough for now. We'll catch you all back here in the next LDI.